Welcome back. Last time we learned how to find the limit of a function from its graph, but how do we find the limit of a function without its graph? How do we find the limit with just the function and the limit notation? And the bottom line is that we just have to plug in the value of x into the function that we're taking the limit of. And sometimes that requires some manipulation, but we're just going to be looking at the basics. And so we'll start with our basic rules that allow us to plug in that x value. So our first basic rule of evaluating limits is that the limit as x approaches some value a of a constant, it's always going to be equal to that same constant. And so what that means is if I had a limit as x approaches, let's say 2 of the function 3, the answer is always going to be 3 no matter what this value of x is, right? No matter what value we're approaching of x, if we are evaluating a function that is just a constant, it's always going to be that constant. And that's because if we graph that function is going to be 3 forever, right? No matter where we go, that function is just going to be 3. So it doesn't matter what value we're approaching, it will always be 3. The second rule is that for a limit where x approaches some number or some value c of x, the function x, the answer is always going to be c. So for example, if we had to limit as x approaches 2 of the function x, we would just plug in this 2 right into this x, and our answer would be 2, right? Whatever this value of c is going to be the answer when plugging it in to x. And our third basic rule for evaluating limits is that if we have a limit as x approaches some value c of a function x to the n power, right? That could be any number. It could be a 1/2 power, which would be a square root, or it could be 2, right? Just x squared. Then our answer would be c to that power that x was raised to. So for example, if we have the limit as x approaches 2 of x squared, that would be equal to 2 squared, which would be equal to 4. And so these three basic rules kind of summarize why we're allowed to just simply plug in values into a limit of a function. It's also important to note that these rules 2 and 3 also apply to other functions other than just x, right? This would work for square root functions, this would work for trigonometric functions, it would work for whatever function you may be taking a limit of. You can simply just plug that value of x in to see what your limit is. Now that may cause some issues down the road where you have an undefined value, but we'll look at that in the next lesson. For now, we're just looking at simple limits that can be evaluated by simply plugging in. So before we get into examples, we also have to talk about the properties that limits have. So limits, just like many concepts in math, have certain properties that we can use. So to kind of get a better idea of these properties, we're going to first define, let's just say, for example, that the limit as x approaches c for the function f of x is equal to L, and that the limit as x approaches c for some function g of x is going to be equal to m. And so L and m just represent the limit of each of these functions at a certain point c. And so we'll start by looking at our first property, and we'll use those two limits to kind of help us visualize what's going on. So our first property has to deal with scalar multiples. So if we have a limit as x approaches some value c for a function that is multiplied by some scalar, such as b, where b is any constant, such as 2 or 3, we could say that this is equal to that constant or scalar times the limit of that function. In this case, it would be L, right? So we have our scalar times the function's limit, which is right here, L. And so that's where this comes from. And so an example of this would be the limit as x approaches 2 of 2x. This would be equal to writing 2 times the limit as x approaches 2 of x, which, as we learned from our rules earlier, is equal to 2. So then we would say it's 2 times 2, and that equals 4. Our second property has to deal with sums and differences. And this one says that if we have a limit as x approaches c of a function plus another function, in this case f of x and g of x, then that would be equal to their limits summed, right? So the limit of f of x is L, and the limit of g of x is m, so our answer would be L plus m. And then this would also work for differences. So if we had the limit of the function f of x minus the function g of x, that would be equal to L minus m. So it works both ways. But for a quick example with the sum property, if L equaled 1 and m equaled 2, then our limit would be 1 plus 2, which would be 3. Our third property deals with products. In this one, we have the limit as x approaches c of f of x multiplied by g of x. And in this case, the limit is going to be equal to the limit of f of x times the limit of g of x. So this would be L times m. So if L equals 2 and m equals 3, for example, then our answer would be 2 times 3, which would give us an answer of 6. For our fourth property, and there's only 5, so we're almost done. Our fourth property is quotient, or deals with quotients. And in this case, we have the limit as x approaches c of f of x divided by g of x is going to be equal to the limit of f of x divided by the limit of g of x. So in this case, it would be L over m. Now this has an extra rule. This only works provided that the limit of g of x, right, or that limit m is not 0. So this is given that m doesn't equal 0, because if it did, then we'd have 0 in the denominator, which would make this value undefined, and so therefore the property would not be true, and the limit would not exist. So then for our fifth property and final property, we have our power property. And this says that if we have a limit as x approaches c for some function, right, in this case f of x, that is being raised to the n power, that would be equal to the limit of that function L to that same power. So for example, if that L, right, if the limit as x approached c for f of x is equal to L, let's say that was equal to 3, then that means that the limit as x approaches c of the function f of x to, let's say, the third power, that would be equal to that limit L, 3, to the third power, which would be 27. All right, now that we looked at all the properties of limits, we can now get into how to evaluate them and do some examples. So we'll start with this example. We'll be looking at the limit as x approaches 2 of the function 3x squared plus 4. And all we have to do this is plug in 2. Now I'm going to show you the long way first, and then I'll show you the very quick way that you can do this after seeing this way. So this would be equal to the limit as x approaches 2 of 3x squared plus the limit as x approaches 2 of 4, right? We can use our sum property to split up this limit into two separate limits, because the sum property says if we have two functions that we're taking the limit of at that same point, in this case x equals 2, then the limit of both of those functions added together is going to be equal to those two functions' limits added together. So because we can do that, we can then take the limit of each part separately. So in this case, we can start with the limit as x approaches 2 of 3x squared, and we plug in our 2, and we find that that is equal to 3 times 2 squared, and then the limit of a constant, no matter what that value of x is always going to be the constant here, 4, so we can write 4. And then we can finish by writing 3 times 4, which is 2 squared, plus 4, and that is going to be equal to 12 plus 4, which is equal to 16, and that would be our final answer for that limit. So now that we did it the long way, that's kind of the hard way to do it, we'll look at the quick and easy way. So we had the limit as x approaches 2 of 3x squared plus 4. We can just simply right away plug in that 2 without having to split it up. We can just take advantage of the fact that we know that the sum property is true and just plug in to both functions. So we'll plug it in, we'll have 3 times 2 squared plus 4, and that is going to be equal to, as we saw before, 3 times 4 plus 4, which is equal to 16. So we get the same answer either way. And so for our second example, we're going to be looking at the limit as x approaches 3 for the function square root of 13 plus x. And so all we have to do to solve this, or to evaluate it, is to plug in that value of x into the function. So we have our square root of 13 plus 3, and that's equal to the square root of 16, which we know is 4, which would be our final answer for this example. All right, we're going to do another example here, and in this example we're going to see that you can plug in the value of x into a rational function as well. So in this case we're going to be looking at the limit as x approaches 1 of the function x squared plus 2x plus 1 all over x plus 2. And just like the other limits, to solve this one we can just plug in 1. And so we're going to get 1 squared plus 2 times 1 plus 1 all over 1 plus 2. That's going to be equal to 1 plus 2 plus 1 over 3, which is going to be equal to 4 over 3. And so we have our answer of 4/3 for that limit. And this is actually a good example to see our quotient property in action. We have a function in the numerator and a function in the denominator, and we plugged 1 into both of them, found their limits, and divided. So while we are using those properties in this case, we're not necessarily really thinking about them, we're just kind of plugging in to the function, which is the nice thing about the properties. They are fairly intuitive. So now that we know how to plug in to solve a limit, let's look at some of those properties a little more explicitly with a new example. So we're going to be given that the limit as x approaches c for the function f of x is going to be equal to 4, and the limit as x approaches c for the function g of x is going to be equal to 3. And so we're going to do 4 different things here. We're going to start with part A. We're going to take the limit as x approaches c of 2 times f of x. So in this case, we already know what the limit of f of x is, and so from our scalar property, we know that we can write 2 times the limit of the function for f of x, and that will get us our answer. So we know that the limit of f of x is 4, and then we know that our answer is going to be 8. And again, this comes from the fact that we can say that the limit of a scalar times a function is equal to the limit of that scalar times the limit of the function, which we know in this case to be 4. Second, we're going to look at the limit as x approaches c for the function f of x plus the function g of x. And our second property tells us that we are able to add the two limits of these functions together to get the limit of that function, right? So in order to find the limit of f of x plus g of x, we can just add the limits of f of x and g of x. So in this case, it would be 4 plus 3, which equals 7. And then for our third part, we're going to be looking at the limit as x approaches c of f of x times g of x. And so for this one, we're going to use the product rule, which says that if we know the limit of f of x and g of x at that point c, we can just multiply these two limits together to get the limit of this function. So in this case, we would have 4 times 3, and that equals 12. And then finally, we'll look at D, which says what is the limit as x approaches c for f of x divided by g of x? What is the limit of that whole function? Well, this uses our quotient rule, which says that we can just take the limit of f of x and divide it by the limit of g of x. In this case, that would be 4 divided by 3, which is actually just our answer. We can't simplify that. Our answer is going to be 4/3. All right, and that's all I had for this lesson on how to evaluate limits. These are all pretty basic limits. If you want to see some more examples, if you feel like you don't quite understand yet, but you need to see a few more, I will have another example video at the end of this that you can click on. You can also find the link to that in the description of this video. So hopefully you learned something. I hope it was helpful, but that's all I have for now, and I will see you next time.